Diffusion and velocity. How does viscosity impact the velocity of a particle during diffusion? By David Wojciechowski, Casey Gerlach, and Jacob Shaner. So a little bit of background information. We decided that the solution with the most viscosity, cornstarch, will produce speeds with the slowest velocity and diffusion time, while the solution with the least viscosity, water, will produce speeds with the fastest velocity and diffusion time. So to test this, we tracked and compared 2 micrometer beads in water, soap, and cornstarch. Using the microscope and software, we were able to record the diffusion beads in each solution by putting drops of each solution onto the microscope one at a time. 2 trials were done for each solution, and the best quality video was selected for each use. Using Tractor, we were able to find the average velocity, and for this experiment, to better compare the results, we used average speed instead of average velocity, which is just the absolute value of average velocity. While the experiment went pretty well, there was a few things that could have manipulated the data. First, bumping the microscope or any surface of the microscope may have disrupted the diffusion speed. Also, the bad video quality that we got at certain times throughout the experiment may have made it difficult to track it. And another thing that could have disrupted it is putting the solution on the plate and then starting the time. That left a little bit of a gap between the starting and the diffusion process, which may have thrown off our data just a little bit. So our models, we have a couple different models that we went through. Conservation energy, we assume that all the kinetic energy in the system is conserved. So all collisions are elastic, the energy is the same, so velocity and mass are kind of the main variables that we're looking at. Since mass is constant, our main focus is the velocity. Diffusion, we kind of know what diffusion is. As particles collide randomly, they will naturally spread from an area of high concentration to an area of low concentration. Using this basic principle, we're able to decide that the viscosity of the solutions will impact the speed of diffusion the greatest. Interactions, the beads run into each other, so as these beads collide, they cause the vectors to change and cause the beads to move from high to low concentrations. Also, we kind of looked at the coding for visual models. We'll go over this a little bit in our data results, but we kind of were able to use code to represent how each solution will look and how the diffusion and the beads will look in each solution. So calculations. We were able to find the x and y values for each bead by using the tracker system, but that's kind of difficult to find average velocity. So with the x and y, we're able to find a c value by using the Pythagorean theorem. With this c value, we're then able to calculate average velocity, which is just c final minus c initial divided by time final minus time initial. After we found each of the average velocity, we can add the 3 beads together and divide it by 3. That will give us like an average of each bead in the solution. A main focus, like I said earlier, we changed average velocity to average speed just to compare it a little easier. So water, we had as the beads in water had the fastest diffusion rate of 8.54 micrometers per second. We can see in this video that the beads move quite fast in water, and we kind of just used computing skills to figure that out. So like I said, compared to other solutions, it moves the fastest, and we kind of decide this because the solution is pure water, there are no additives. So given that the mass and the size of the molecules is small, since it's solely water, that the velocity will be higher. We determine this with the kinetic energy equation, 1/2 mass times velocity squared. So in this example, the diffusion of the beads are not colliding with anything besides water, therefore that the velocity will be much higher. So the next we have is soap. Here is the little model that we created for soap. It's in this model, the beads, which are red, are moving a little bit slower than they were moving in the water solution. And this is what we found in our data. We had an average speed of 4.47 micrometers per second. That was the speed. And we kind of determined this by using the idea that in this solution, we not only have water, but we also have soap molecules. Soap molecules tend to be larger than water molecules, but smaller than cornstarch molecules, which we'll talk about in a little bit later. They're comprised of carbon, oxygen, and hydrogen. So because this solution is not just water, it has more of a chance of running into other molecules, these beads do, therefore decreasing the velocity. The last solution we tried is cornstarch. In this solution, we can see the beads are moving very slow in the cornstarch, and by using our explanation, we have cornstarch is the largest of the 3 molecules, and since it isn't just water but also cornstarch, the beads are more likely to run into these solutions, and we already know that solutions with cornstarch are more sticky, and therefore the velocity is much smaller for the beads in this solution, with only 3.32 micrometers per second. Therefore, in our conclusion here, we have, by comparing the three speeds we calculated from the experiment, we concluded that our hypothesis is correct. The most viscose solution, cornstarch, had the lowest diffusion rate, while the least viscose solution had the fastest diffusion rate.